Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the discussions on exergy destruction. Irreversibilities such as friction, mixing, chemical reactions, heat transfer through a finite temperature difference, unrestrained expansion, non-quasi-equilibrium compression, or expansion always generate entropy, and anything that generates entropy always destroys exergy. The exergy destroyed is proportional to the entropy generated and is expressed as. Note that exergy destroyed is a positive quantity for any actual process and becomes zero for a reversible process. Exergy destroyed represents the last work potential and is also called the irreversibility or last work. The decrease of exergy and the exergy destruction are applicable to any kind of system undergoing any kind of process, since any system and its surroundings can be enclosed by a sufficiently large arbitrary boundary across which there is no heat, work, and mass transfer, and thus any system and its surroundings constitute an isolated system. No actual process is truly reversible, and thus some exergy is destroyed during a process. The more irreversibility a process is, the larger the exergy destruction during that process. No exergy is destroyed during a reversible process. The same calculation formula is obtained for the loss of heat exergy, flowing working fluid exergy, or working fluid exergy in an irreversible process. Although this is obtained under different circumstances, in fact, the above formula is indeed generally correct. Any loss is equal to the entropy increase of the isolated system and the ambient temperature. The usable energy loss caused by various irreversible factors is different from the power loss caused by friction. Even in the case where the irreversible loss of the isolated system is entirely caused by power loss, the loss of usable energy is not necessarily equal to the power loss. If the temperature of heat production due to power loss is higher than the ambient temperature, then this part of heat production still has a working potential to the environment. That is, it has available energy. At this time, exergy destruction is less than power loss. Only when the heat produced by power loss is all waste heat, exergy destruction equals power loss. The topic of this subtask is about the decrease of exergy principle. We have established the increase of entropy principle, which can be regarded as one of the statements of the second law, and we indicated that entropy can be created but cannot be destroyed. That is, entropy generation SGEN must be positive or zero, but it cannot be negative. Now, we are about to establish an alternative statement of the second law called the decrease of exergy principle, which is the counterpart of the increase of entropy principle. Consider a stationary, isolated system. By definition, no heat, work, or mass can cross the boundaries of an isolated system, and thus there is no energy and entropy transfer. The energy balance for an isolated system can be expressed as the entropy balance for an isolated system can be expressed as for an isolated system, the exergy change is. This equation can be expressed as the exergy of an isolated system during a process always decreases, or in the limiting case of a reversible case, remains constant. In other words, it never increases, and exergy is destroyed during an actual process. This is known as the decrease of exergy principle. For an isolated system, the decrease in exergy is equal to the exergy destroyed. The decrease of exergy principle implies the exergy of an isolated system during a process always decreases, or in the limiting case of a reversible case, remains constant. In other words, it never increases, and exergy is destroyed during an actual process. The decrease of exergy principle does not imply that the exergy of a system cannot increase. The exergy change of a system can be positive or negative during a process, but exergy destroyed cannot be negative. Okay, that's all for this task. Thank you very much, and see you next time.